Hello everyone, my name is Devashish and I am a PhD scholar at Indian Institute of Technology Madras, and today I will present our work on aeroelastic analysis of span morphing wing with moving loads. So this will be our outline for the entire presentation. So the idea behind morphing wing is to maximize the aircraft performance during multiple flight conditions by changing the geometry of the wing. In literature, there are many types of morphing concepts available, but for our study, among all of those concepts, we have chosen one most promising concept, that is span morphing. The design of span morphing wing involves many challenges, such as developing the appropriate physical morphing mechanism, then mathematically modeling of that mechanism, then experimental validation, etc. Many studies have focused on developing the physical mechanisms, but most of these were focused on performance characteristics analysis. In 2005, Wei and his group studied the static aeroelasticity of a span morphing UAV. In that study, they have assumed the span to increase in discrete time step. In 2014, Murugan and his group developed a telescopic box beam type span morphing wing and derived the dynamic aeroelastic model for it. In 2020, Daniel and Murugan studied the structural dynamic effects of span morphing wing by modeling it as a moving load problem. In this current study, our idea is to develop a dynamic aeroelastic model of a span morphing wing as a moving load dynamic problem and study the responses for various loading cases. So now we can see a typical telescopic beam mechanism consisting of two beams. One is the host beam, which is fixed at its root to the fuselage. Second one is a sliding beam, which is fixed at its root to a slider, which slides over the host beam. In a typical UAV wing, the wing is subjected to aerodynamic forces and a torque due to the aerodynamic moments. Now we have considered that the joints between the sliding beam and the host beam are efficiently allowing the transfer of loads from the sliding beam to the host beam. So in our study, we have replaced the sliding beam and its aerodynamic loads by a combination of moving loads, especially a moving force, a moving moment, and a moving torque. Now, mathematically, to capture the effect of the moving loads in the equations, we have used direct delta function. The formulation is on screen, you can see, where v is the morphing speed, and with the same speed, moving loads will move on the host beam. For the Lagrangian formulation, we have used Euler-Bernoulli beam theory, where the dynamic response is represented by coupled bending and torsional modes associated with respective generalized coordinates. For the numerical simulation, we have used two orthogonal modes of bending and two orthogonal modes of torsion. The incremental work done over the wing have contribution from moving loads in addition to the aerodynamic lift and aerodynamic moment. And using Lagrange equation, the complete aeroelastic equation of motion is obtained like this. Now for numerical simulation, we have considered two scenarios. In the first one, we have studied the dynamic response of the host beam due to the morphing effects with zero initial condition. No aerodynamic forces was considered in this case. In the second one, we have studied the aeroelastic response of the host beam with zero initial conditions. Apart from these, on the basis of morphing speed, we have also classified into two cases. First one is the slow speed of morphing, where the moving loads are traversing lesser than the critical velocity. Second one is the fast speed, where the moving loads are traversing higher than the critical velocity. Now we'll see the dynamic bending response of the tip of the host beam due to the morphing effects only. Now Q1 and Q2 here is the generalized coordinate associated with first and second mode of bending respectively. Now we can see the Q2, that is the second mode of bending, is dominant over the bending response. Now we can see during morphing process, the amplitude of the oscillatory bending response reaches its maximum well before the loads reaching the tip, and when the loads reaches the tip, the response shows sustained harmonic oscillation. Post-morphing process for slowly moving loads, the maximum amplitude is 19% more, where a fast moving loads, the maximum amplitude is 28% more than a normal wing. We have seen the dynamic bending response for the tip of the host beam. Now we'll see the aeroelastic bending response, where we have considered the aerodynamic forces also. Here also we can see the second mode of bending is dominant in overall bending response. During morphing process, bending response increases till the loads reaches up to the two-thirds of the span and then decays down gradually for the rest of the travel time. But during morphing, the peak amplitude we got in the aeroelastic response is 9 to 11% lesser than the dynamic response we got earlier. This is all because the aerodynamic damping. Post-morphing process also, the harmonic oscillatory motion decays down to a steady state value due to aerodynamic damping. But for fastly moving loads, the oscillations sustain for a longer time period. Post-morphing process, for slowly moving loads, the maximum amplitude is 125% more than wing without moving loads and 137.5% more for the fastly moving case. Now we can see dynamic torsional response of the host beam. Here also we can see the second mode of torsion, that is Q4, is dominant over the torsional response. We can see during morphing process the amplitude of the harmonic oscillatory response decreases gradually, and post-morphing process the maximum amplitude is lesser than the normal wings response. For slowly moving loads it is 99% lesser, and for a fast moving loads it is 90% lesser. We have seen the dynamic torsional response. Now we will see the aeroelastic torsional response. The nature of the response is almost same. Here also the second mode of torsion is dominant in the overall torsional response. But in the during morphing process, we can see the peak amplitude in the aeroelastic torsional response is 7% lesser than the dynamic response we have seen. Same in the post-morphing process also. Post-morphing process, due to aerodynamic damping, the response of the amplitude decreases gradually. In the post-morphing process, the slowly moving loads, the amplitude is 98% lesser as compared to normal wing. And for the fastly moving load, it is 85% lesser. Now to summarize our work, so first we have done a dynamic and aeroelastic model of a span morphing wing developed on the idea based on a moving load problem. Then we have numerically simulated the response of the wing during morphing and post-morphing process. We have also seen that the aeroelastic response is always lesser than the dynamic response of the host beam. This is just because of aerodynamic damping. Then we have seen that post-morphing process, the maximum amplitude of the bending response of the host beam is always more than a wing without a moving loads, that is a normal wing. But we have seen a contrasting characteristics for a torsional response. We have seen for torsional response, post-morphing process, the maximum amplitude is lesser than a normal wing response. We have also seen that for loads moving at high speed, the dynamic nature in the response is very much less significant. Whereas loads moving at slow speed, we have seen the dynamic nature in the response is very much significant. In this work, we have only considered in the expansion process of the morphing mechanism, but we have not considered the contraction process. So we are currently working on the response of the wing during the contraction process, and simultaneously we are working on stability and control analysis of the wing. That's it from our side. Thank you. If you have any question, we will be happy to answer that.